Click the bell icon to get latest videos from Ekeeda.
Hello friends, today we will discuss about intra-operation parallelism. That is, inside an operation, how can we divide it within a parallel nature? First, we will know about how to partition it within this range partition, the external sort merge algorithm. Then we will know each of the operations like the joining operation with parallel, partition join, hash join, replicate and fragmenting join, nested loop join, and all other operations and the cost related to the operations that can be happen inside this intra-operation parallelism. Intraoperation parallelism happens when we want that one operation to be parallelized into different processor. Say that within a query we can have different operations which can process and execute in different type of processors and different part of the disk on this they are storing. Now, when we are talking about that one operations which can have many tuples, that a large database can have many tuples, at least thousands of tuples on which we need to perform the operation, then we must divide the operation into different sections. So suppose the selection operation that we are talking about, and it is on thousands of database that we are using. So now we can divide the database by partitioning into separate disk and perform the selection operation, the same operation into different partitions so that we can have the result and as a final result all the joining of them. Now this is known about intra-operation parallelism because now one operation is in parallelly executing at all parts or different partitions. So the term in intra-operation is more related is the term partition or the disk partitions. So before any parallelism can be performed on the disk that is storing an intra-operations or the database that is stored into different disk partitions, we can consider D0 to Dn-1 number of disks that are storing the different database partitions, where n is the number of disks. Now we can say that we want to parallelly sort this D0 to Dn-1. So we can have that each of these disks will be parallelly sorted, and finally from the disk we can sort it, find to the exact database sorting. Now the sorting can be of two types. One is the parallel sort, another is an external sort merge algorithm. So now as we know that the partition can be ranging partition or can be category partitions. So it is on an attribute partition, then we choose the external sort merge algorithm, and if the already partitions are based on a range condition, then we must choose the range partition. So first we will talk about the parallel range partitions. So the range partitioning is done in two steps. First, we need to partition them inside of a range on each of the disk partitions, and finally then each of the partitions will be merged together to have the final parallel sort. Now how to make this one? We can create each of the disk or many of the disks to be run on different processors. Because of the intra operation or this intra query nature, we want that every operations on a large database, if they can occur on different part or different processor, then the computation time will be much lesser. So now if we have this processor P0, P1 to Pn-1, now the n can be confused with this number of disks, so we can make this as m-1. That means now we can have m number of processors and n number of disks associated to it. Now obviously while moving to this m and n, we have m equals to number of processors. And one more condition then we need to put, that is m is obviously less than n, because if there are more number of processors than the disk, then it will be no use if we divide the task into the processors. So there will be always lesser number of processors than the disk on which the data are being partitioned. So in steps 1, we can perform that. First we need that if there is an ith tuple that it stores in this di, then we must make it to this pi on this ith tuple. Say we are talking about the tuple isti. So now the any tuple that belongs to this ti disk, and the pi disk is processing this ti tuple. So for any range that is I from 1 to say k, we bring all ti to this di and finally to pi to make the disk partitioned over the processor pi. So now finally on this pi to pm, for di to dn, we make all the ti to tk. That means every tuple or I to k set that belongs to di, dj, dk to dn will be now bring back to pi, pj, pm, pn like this. So now after range over partitioning, we need to sort the data. Now each of the data inside a processor need to be parallelized sort, and this is known as data parallelism. So this is now more concerned with the data, not the condition or the operation that we are having. So what is the basic use of sorting the data? If you sort the data, it will not only reduce the time of the operation, but it will also leave the complex structure of an operation be in a simple way. Now how we can provide this? Say the operation is sorted and now I want to go for the salary ranges of 0 to 50,000. So we can directly go over a partition that is already sorted down and find the maximum or minimum of the salary belonging to the sorted list. So now for the data parallelism, we choose supple and this tuple that we are swapping on the particular disk. After the disk that has been partitioned, we need to rejoin the disk according to the sorted algorithm. Now we can sort the data in this way that I must be greater than equals to 1 and j must be greater than equals to m in this way that pi will always have value less than pj. That means any tuple that belongs to the di and goes in the processor pi will be less than in value that goes in pj will have the value on dj. That means now my disk I is partitioned a lower partition on the dj that is having a higher range partition. So in this way we can have our final partition that our database is now sorted over the disk and the processors. Now, if it is not in the range partitioning, based on category partitioning, it is being partitioned already. Now we will choose the external sort merge algorithm. Now the external sort merge algorithm based on a categorical or attribute partitioning. Now we have at steps 1 that internally we need to partition among this sorting of disk di to dn minus 1. So first from d0 to dn minus 1, all the disk data we need to sort, and finally we need to merge the sorted data disk in such a way that the system will consist the final db as an sorted one. So we need to merge this d0 to dn minus 1 so that we can have the external sort merge algorithm. Now how to merge this one? So the steps 2 needs another steps to be performed. First we need to find the processor that belongs to p0 to pm minus 1, where we had the previous condition m is less than equals to n. Now we can have this p0 to pm minus 1, through which we need to find pi in such a way that it belongs that for all pi and the tuple that belongs to this ti is less than the tuple that belongs to this ti plus 1. That means now inside it we find the relation ti is less than ti plus 1. So it is like sorting the internal data. Now after that pi merges all the data based on a sorted single run. So now pi merges with pj based on the conditions that all ti must be less than pj. Now it can do within short merge algorithm, like first we need to give all the tuples ti and then compare with the tuple tj. If each ti is less than tj, then we will merge it on this pi, and if it is not, then we will have all the ti to tn minus 1 completed, and then finally continue with tj to tj minus 1. Now in which the pi merges with pj. Finally, as a result, we will have all p0 to pm minus 1 merges with each other in a single sorted run. So in this way, we can perform the external sort merge run to get the parallel result onto this sorted one. So now we are having unsorted data in each of the disk and in each of the processor, on which we can perform our operation, at least one operation separately on each data. So now when we are performing this external sort merge algorithm, as we are talking about an intra operation, that means here we are not considering the execution of parallel operation. Here we are parallelizing the execution of one operation. That is the exactly opposite of an interoperation parallelism. While we know that the interoperation and intraoperation parallelism can go hand in hand with each other, but the problem with this type of external sort merge algorithm is the execution skew. Like in the execution skew, what happened? Just consider this one with every tuple. So now we can see that the partition 0 belongs to P0, the partition 1 belongs to P1. Like this, the partition n belongs to Pm minus 1. Now every tuple, when it is executing, then you have this T0 first, and then we can have T0 plus 1 T1 in P0. Like in P1 also, the second tuple can be executed only after the P0 has been sorted with the P1. Because now P0 will have all the values, that is Ti less than Tj, so we cannot execute P0 before Pj or before P1 and also with P1. So now we need to execute P0 and P1 sequentially, which is becoming a skew to this Pm minus 1. Like the Pm minus processor need to wait for P0, P1 to Pm minus 2 processor to finish their execution. This is a main problem with an external sort merge algorithm. So it becoming a skew for the last processor or the next processor. We are waiting for this first processor to get processed in. Next, we will talking about after the partitioning is done and the sorted result is being performed, we're talking about the join operation. Now the join that we will perform is in parallel join. So when we are having a parallel join, that means we can parallelly first partition the data and then join it. What is the meaning of the first partitioning and then joining? Now we are partitioning a relation and then joining two relations. So the main difference lies in here, that the partitioning is not on the joined relation but each individual relations. So the first type of joining on a parallel join that we will discuss is a parallel partition join. Now in parallel partition join, what we do, we first partition each of this relation and then perform the joining on which, based on some range partitioning join or hash partitioning join. So first we need to partition each of this relation. Say suppose that we want to join R and S. Now we want to perform the partitioning from R0 to Rn minus 1 and say S0 to Sn minus 1. Now what happens that for processor Pi, it sends the request to get processor Ri and Si, their data result, to the Pi. So the relational extent partition of Ri and Si now goes to Pi. Now Pi partition and join them on Ri and Si. Now this joining can based on the any condition like the range partitioning joining or the hash partitioning joining. First we will talk about the range partitioning joining. Now if it is an equi-join that we are having, that means we are having the condition R joining S, such as R joining R dot A equals to S dot B with S. So now we can have that R and S has been equity joining. That means some attribute values is equals to the values of S. Then we can join R and S. Now this type of joining is becoming easy because now we can have the attribute matched with each other from each of the partitions and then join them together in a partition join. Now for range partitioning, we need to find the same partition vector for each of the partition. Say for an example, when we are joining, say the partition vector belongs to the range of 50,000. Say we are having the salary and the range is 50,000. That means it go with 0 to 50,000, 50,000 to 1 lakh, and so on. So now the partition vector should be same for each of this partitioning. Now inside the hash partitioning, we should choose the same hash function for each of this one. Like if we are going with the salary and we are using a hash function, then we can choose di mod I. That means we are modding with the number of this that is present there. So now in this way also we can choose the same hash function for each of the partition. Now if we are choosing the different vectors and hash partitioning function for the different partition, then we will not have our join done because now we will have a different result in each of the partitions. Now we can see that how we can exemplify our partition parallel join. Say suppose we have these two relations R and S. Now we have the partitions for R as R0, R1, R2, R3. And for S again we have S0 to S3 and more. Now we have on the based on hash partitioning or the range partitioning some of the instance. Say these are the instance of R or the tuples and these are the instances of S. Now some goes to R0, some goes to R1 and for S0 too. So now we have the tuples arranged in this partition based on either a range or an hash partition. Now after the partition has been created, we can either use the nested loop join, the merge join, the hash join, the partition join, any of these techniques to join these two relations. Now this R0 and S0 moves with this P0 processor. So now after the partition is being done, then P0 will partition join on this R0 and S0. So as with R1, R2 and R3. So in this way, we can parallelly partition join our relations. So what we need to do, first we need to select the tuples. Say this is the Ti to Tk tuples from S. From Ti to Tk that belongs to each of the relation R. Now we can say that the relation that is having the tuple T and can also have the tuple S now joined together inside a processor Pi which belongs from P0 to Pm. So we can see that there is some way partitioning need to be done between the relation. If the partitioning is already there, then it is no way a problem just to join them inside each of the processor. But if the partitioning is not being done, then we need to first partition it and then perform the joining. So how can we partition inside the processor? First we need to fetch from each Ti that belongs to R. I'm not saying here Ri because it is not partitioned till now. So first Ti is being fetched to R and also from this Ti that is fetched to S. Now each of these R and S go with process Pi. And now the process Pi shorts this Ti and make the partitions Ri and Si inside this Pi. So now we are not having this R0 and S0 joined with P0. We have some tuples, say set I to K minus 1 and some tuples say J to K minus 1 from R and S. Now these two tuple sets are given to processor Pi which then partition them for R0 and S0. Then join them with an Pi processor. So in this way we can process the parallel partition join and can make the join successful on becoming the partition bin the or attribute way or the categorical way. So now the total size of the joining will be the size on the partitions base. That means the size will be Ri plus Si for a joining which is made on say P0. For Pi it will be Ri plus Si. So the size of R with the summation with the size of S will be the processor size to short the relation. Now we will go to the next part, that is fragment replicated join. Now what happens if it is not belonging to some range partitioning and it is done in a categorical way? So we cannot just have in the category that each category belong to a range. Say suppose that we are name wise or say city name or city state wise made the partitioning. So now we have West Bengal, Mumbai, Delhi is this type of states and then can have the partition made. So what happens that if someone belonging to the same state belongs to other departments, so in which category we are making the partition is becoming extremely important while having the fragment replicated join. So for the fragment replicated join, we have first the categorical information. Now this fragment replicated join for the category that we are seeing, not on an equality basis that we are having the join. So now my R join S stands for R join R dot A, that is somewhere less than S dot B on S. That means there exists some values on attribute on A which relates with S in that matter that it is less than the value of the attribute B. Now it can have every attribute that can be in one partition that is less than one another attribute from S. Now what happens, and if this is becoming very difficult because there can be many ranges or many categories on which this type of inequality can exist. Say suppose for example that if someone is going to the 40,000 salary, then they can go within the range of less than 75,000. Now if someone is having the salary 20,000, then they can also give the range of this one, and also someone who is having 10 salary, then also they can belong to the range of this one. Finally 74,000 can also belong to the range of this one. So now this provides us with a scenario where we can have no categorical information because the range is 10, 20,000, 40,000 and 74,000 goes in a huge partition. And if I want to make a partition with less than 75,000, it will be extremely problematic to fetch all the values that is less than B. So now we need to choose A in such a way that this less than comparison becomes a logical partitioning among the data. Now the first one is an asymmetric fragment replicate join. So when we are having this type of data, then we can choose the fragment replicate join or asymmetric fragment replicate join. Now in asymmetric fragment replicate join, it first divides the R and S both the relation and replicates the data inside a partition. Now we can choose for both of this relation any partitioning technique, say for the round robin technique, the range partitioning technique or the category partitioning technique. Say I am taking the round robin technique. Whatever technique we are choosing for relation R, we need to choose the relation for S too. So now for R and S both are having this round robin technique for partitioning. Now we are joining at the second step this Ri that we had partitions with the processor Pi relation Si. Now this is more like the parallel partitioning join with the difference that in here we need to make the partition not within range or not within category but within periodically checking that can be a logical transformation on this one. Say suppose that values 40,000, 25,000 belongs to a category and 10 and 74,000 belongs to other category. So what happens when we put this two in one section and this two in another section? So it becomes a range of 10 and 74,000 that we cannot sort and cannot get a logical reason to have this. That is why we cannot choose the parallel partition join. Rather, we go for this asymmetric replicate join. First, we fragment them and then we replicate the data for each of this relation that we need to join. So now for each of the relation that R0, R1, R2, R3, we will join that with S1, that is some relation with S1. So now how to represent this fragment replicate asymmetric joining? Say for an instance, we have 4 partitions on the relation R. And for this 4 partition, that is R0, R1, R2, R3. So for each of the instances R0, we need to find to the relation S. That means now my Si becomes the whole S. So now for my R0, we use an processor P0 to go and check for some of the relations in S that make it comparable with this R0 partitioning. That means we first need to partition in a logical way with the relation R, and then the processor on the P0 or the Pi to find the possible relations with S. Like for this relation also, we need to find another P1 which will join with another instances of set S. So what we are doing, that we are fragmenting one relation and then replicating the value inside this S. So what is the disadvantage of such situations? That first we need to fragment it, which is fine for the partitioning purpose, but we need to replicate the data of this partition inside this processor, which we have the S relation at a whole. That means we need to compare each tuple of this partitioning with each tuple of S so that we can build some logical comparison that satisfy this equity or this inequity that we can have inside this joining. Now, other than having this fragment replicated join, we can have the asymmetric one as one contrast with this one. What we are having, we are dividing both R and S into the sets of R0 to Rn-1 and S0 to Sn-1. And finally, we are replicating the values of each of these instances of R0 with the S0 to S-1. So now we are partitioning both R and S. That will improve our functionality, as we do not need to sort each of these functions on these partitions, because they are coming with an external merge sort algorithm that they can have inside these partitions that we join with another range of the partitions. So now let us join this external merge sort algorithm uses this fragment replicate and join. Now we see that the m and n doesn't need to be equal. All we need that the m cross n processors, because we can have for each S0 the relation of R0 to Rn-1, and for each S0 the relation S0 to Sm-1. So now we can have that R partition to n-1 and S partition to m-1. But we can see that this fragment replicate join just reduces the size of the processors, because now we do not need that the processor will have all the replications from R0 and all the tuples from S. Again, the processor Pi plus 1 will have all the processors from R1 and all the tuples from S. So now we can have a combination of the partition that reduces the size of the processor. So here in this S0, we can have P00. That means now we are having an Pij combination where we can connect with the S0 and R0. Same we can have P0, 1 to have the instances of R0 and S1. So what we are doing, that we are P0 dividing it to P0 to Pm-1. P1 dividing it to P0 to Pj-1. So in this way, for every data, we are having the replication on the fragmentation of the second relation too. So that all results are joined together. So in this way, we can generate all the processors as a combination of this one. I'm not showing all the combinations because it is more like same. So here it is considered to be a two-dimensional matrix where we can show the ij in such a way that Ri and Sj belongs a pair where we can have the replications of all R0 that matches with the S0. Now here again I am mentioning that the partitioning become extremely useful for the logical reasoning, because other than having the R0 and S0 properly partitioned, this joining will have no meaning because it is replicating the value. That means it's taking up size of the memory. The next one is the partitioned parallel hash join. Now we are considering two relations S and R in that way that the size of S is the less than the size of R. We have the processors P0 to Pm-1 to be divided in the disk and partitioned. Now we will build our hash functions H1 in such this. Now what happens that every tuple Ti that belongs to the Di must be made to the processor Pi and maps it to the tuple Ti that belongs to the Si. Say suppose that the Ti which belongs to Di now being mapped to the Ti which belongs to Di. Now this Ti belongs to the Ri and this one to this Si. So now we can say that the processor Pi is having tuple matched with each other from R and one is from S. Now this mapping is done basically with the hash function. So first we need to build an hash functions that is to be calculated on each of the tuple for R and S both, and then use the hash functions to join the value in the processor Pi for each partitions on Ri and Si. Now the processor Pi has all the partitions for Si. Now with the hash functions H2, it again partitions Si. That means now say my tuple of Si is in set of say TUI plus 1 like this. Now Si builds an H on this TU and then creates another set Sj which is consist of Si plus 1 till Si plus n. So now in this way the second step is that furthermore partitioning we are joining based on another hash function. That means my H2 is now being created with this one and H1 is being the initial one. Now as we know that S's size is lesser than the relation size of R. Now what happens that R is the larger one. Now we have the partitions of Ri and the Si is partitioned into H2. So again we need to compute the H1 on Ri and the H2 on Rj plus 1. So first we need to build this H1 relation hash function on every tuple T that belongs to the set Ri, and now on this Ri again we need to build an hash function H2 Tj with sets of Rj plus 1 till Ri. So now we have this Ri again partitioned into this H2. Now what is the difference between the R and S? Because there will be higher number of Ri than Si. So my Si is less than Ri, just like my S is less than R. Now my Pi probe into Ri and Si both so that they can have joined them onto an hash function built on H1 and H2. So now Pi probe on Ri and Si and H1 and H2 as a final result which can be created on the partition and join them on R and S. So this is the parallel partition hash joining. So why it is parallelly joining? Because we can have the partition on R and the partition on S at the same time onto two different processors, so that we can have this hash functions that is made on the R and S both at the same time. Now the hash functions we will be need another processor to probe into that hash functions of the final partitions and Ri and Si and to make the joining of R and S. The next one is the parallel nested loop joining. Now the parallel nested loop joining is just like the nested loop joining in that way that every part of the nested loop join will be executing parallelly. Say for an instance that we have for each I that belongs to Ri, we can have generated say a range partition on which we have for each j that belong to Sj. Now we are joining them on Ri, join Sj. Now this can be a hash join, merge join or anything. But inside this nested loop join, when we are performing this as parallelly, we need to remodify the statements. So now nestedly, we need to replicate all the data of R and S executed concurrently and then have the join as the final one. Say we are now for each k in relation R where we have pi that belongs to the range pk to pk plus n. That means now we have one more with the processor that will be considered as a final processor. As Ring is the size greater than this S, then we can have for each I in R. Other than if S is the higher one, we can put this S here. Now this for loop which is being nested with this loop can be concurrently executed with another loop that we am writing. So first for each I in R, we need to join the R within fragment replicate. That means we need to find each tuple Ti that belongs to R and then join to Ti to Pi in such a way that replicate S. That means for each Pi, we are replicating the tuple Ti that belongs to R and we are replicating it with an Si. That means all combination of Si like T0 with S, T1 with S is being performed. Now we are having this for each I in R. Same goes with for each J in S where we have Tj belongs to S such that we are replicating Tj to S with every possible tuple that belongs to R. So now we are having Tj with R, Tj plus 1 with R in this way. So suppose that any values which goes in the k in R, that means finally we are having the R as the final one. So now the Ti belongs to R and Tj belongs to S, both can execute concurrently under the nested loop for each k in R. That means finally my R will be the ultimate relation to join the replication from R and S, and then it will be compared either with an equality or non-equality operations with this R and S joining. So in this way we can perform the join operation on a parallel using the partition join, fragment replication join, nested loop join and hash join are the operations that we are having on selection, projection, aggregation and all. Now first let us consider the selection operation. Say the selection is for a relation theta, it is R. Now how it can be handled inside an intraoperation parallelism, or we can say that we are having it inside an parallel joining. So the selection on theta if the condition is on equality. Say suppose where ai is the attribute and v is the value to it, and that is the basis of this theta joining. Then we have all the ranges that belongs to v in this type of selection. Other than we can have a range selection so that we can have. So in this type also we are having this intraoperation parallelism. Say suppose that ai equals to v goes for the city name. That means we are having the city wise operation on selection, or we can have the salary wise selection like from 0 to 50,000, 50 to 1 lakh, like this one. So L and U are the lower and upper limit for the selection. The next is the projection. Now the projection operation and how we can handle in an intra operation, because the projection and say suppose there is also a condition the projection. So we first need to select it and then we can perform the projection. So the projection with theta implies that there is a selection of theta on which we can perform the projection. So it is more like the selection operation. The next is the aggregation operation. Well, it is extremely difficult to handle the aggregation operation in an intra operation because we can perform the partition, say for A to C, D to F, there are partitions, and every aggregation that, say, the count operation we are performing. So if it is based on a range, then it is extremely easy to count the values and then combine the values. But if it is category wise, then final combination becomes impossible inside this intra operation, and we need to again range partition the category wise and then perform the counting. So these are the operations that other than the joining and sorting we can perform in an intra operation parallelism. The final one is the cost of these operations. Now there are many costs that is assembled to it. First is the total cost. That means all the operation need to be considered individually and the summation of the cost. Next is the skew cost. As in the parallel external sort algorithm, we have seen that there is a cost for execution skew, that every pipeline need to wait for the queue and the pipelining result of the previous result. So now we need to wait, and the CPU cycles waste cost are much larger. Now next one is the cost of assembling. Now if we have the transaction as a part of T part, and there is a cost of assembling, that means we are assembling all the partitions again. So for partitioning there is a cost, first for assembling there is a cost, and then we need to choose the maximum cost of the transaction that is happening on every partition. So we need to choose T max for the partitions T0 to Tn minus 1. And also there is a contention for the resource, then we need to keep the resource for every partition evenly distributed. Other than this, we cannot have the partitions to be combined together to a meaningful way. So this is all for the cost, the joining and other operation that is related to the intra-operation parallelism. Thank you for watching this video. Stay tuned with Ekeeda and subscribe to Ekeeda.